future-proofing power intent specification through Unified Power Format UPF 4.0 for borrowing advanced state retention strategies. Abstract. This paper discusses the role of the state retention SR elements and strategies in the optimizing power consumption while ensuring quick system recovery. By utilizing IEEE 1801 standard, also known as Unified Power Format UPF, SR can be effectively specified, modeled, verified, and implemented coherently to ensure the functional and electrical correctness under a wide range of operating conditions. Conventional SR techniques as mostly bar the implementation of underlying SR element and SR system-level SR strategy that pass potentially suboptimal for evolving technologies and end applications. Many of these evolve SR strategy for area and power efficiency SR element with a low level, that is, device level optimizations utilized when building such element may impose additional functional and electrical boundary conditions. Comprehensive handling of such boundary conditions is not supported in the current version of the power intent PI standards. In the upcoming version UPF 4.0, we proposed additional statistical features supporting a scalable semantics of evolving advanced SR requirements and techniques for more complex power intent specifications, consistent and coherent interpretation with the seamless handling across the EDA tools and flows. A detailed case study is providing demonstrating practical applications of strategies in low power designs. Introduction. As electronic systems evolve to meet the increasing demand for energy efficiency, especially in mobile and embedded devices, low power design techniques are critical for reducing both dynamic and static power consumption. Standard techniques for realizing the functional and electrical consistency help design with the usual control over power versus performance trade-offs include designing with a suitable metal oxide semiconductor MOS devices of the appropriate gate threshold, adaptive and static body biasing, clock gating for a section of the design for a period of no activity, frequency resisting section of the design for a period of the low power performance, adaptive voltage and frequency scaling, power gating. Additional techniques that are needed to overcome the challenges due to the implementation of any of the aforementioned approaches include isolation of the signals and switchable, that is, power and gate domain to clearly define a safe state for avoiding functional and power consumption issues in the receiving domains that remain powered on. State retention as all of the memory elements in the switchable power domains. Level shifting for signals crossing between the domains in compatible board supply voltage level. Clock and reset domain cross CDC and RDC techniques like clock and reset synchronization respectively. Standardized power intent PI specifications like Common Power Format CPF and IEEE 1801 standard, also known as a Unified Power Format UPF, support the power gating and scaling related aspects. One of the key challenges in power management is maintaining data integrity during power down event B's power shutdown and the various gradation of the sleep modes. SR strategies, particularly the use of the SR element and method, to provide a solution by preserving the critical state information even when the power supply to the parts of the system is turned off. This paper explores the various SR techniques employed in low power, energy-aware systems, including the design and implementation of the SR registers under power-gated system modes. and static saving mechanisms. It discusses the role of the SR element and strategies in optimizing the power consumption while ensuring the quick system recovery and minimal power overhead during power state transitions. By utilizing UPF, SR can be effectively specified as models verified implementally coherently to ensure the functional electrical correctness under a wide range of operating conditions. It delves into verification strategy for design with SR, such as analysis of various power state, checking data integrity across power down cycles, and ensuring the seamless power state transition in complex system on chip SCT giants. Chapter 2: Advanced Retention Challenges. An example LP system, its power-aware verification setup, and the signal level behavior for the system level as the system are illustrated in Figure 1, Figure 2, Figure 3, respectively. They showcase a typical LP system demonstrating the interaction between different power domains and the associated control signals that ensures proper state retention across the power down cycles. The verification flow is integrated in a PA simulation tool that supports simulating the power more complete and power-grained behavior of the system under various power states, exhibiting the conservative behavior by corrupting the state of the logic circuits under such power domains whose surprise are switches of the minimized power consumption and ensuring the state information of the such switches of the power domains can be preserved accurately as if specified appropriately. Figure 1 illustrates an overview of the system architecture, highlighting the role of the power gating, clock gating, and adaptive vertical scaling in managing the dynamic and static power consumption and dissipation. Figure 2 delves deeper insight into the verification process, where each power domain is evaluated functional correctness during both transitions, ensuring that isolation, level shifting, and retention element behave as expected in the presence of the switch's power supplies. Figure 3 illustrates the signal level behavior, emphasizing the interplay between clock reset control signals during transition between active and power down state. This is a Figure 1, the typical LP system. As illustrated in Figure 1 and Figure 3, the switchable domain PD underscore V3 associated with the supply net V4 supplies IP3 requiring state retention. State retention is enabled in the system by asserting the signal RET before the switch powering V4 is turned off by the asserting power domain enabler, and eventually V4 becomes valid. The state D5 encountered at the rising edge of the RET signal is saved and retained during invalid V4, that is, power down state of the IP3. Upon exit from power down by asserting the power domain enablers, once V4 becomes valid and subsequently upon the assertion of the RET and the saved retained state D5 is restored. However, the strategic allows a successful SR operation independent of the clock, CLK, and reset preset RSD G_V4 control signal state during the period between the save and restore event, requiring the underlying SR element having the clock signal clock gated internally with the retention control signal RET. This allows the clock trigger activity when RET remains asserted without causing them any malfunction, including loss of the retained state. Such implementation doesn't pose any constraint on the system-level clock tree, allowing each driver to be powered off and reduce power consumptions or to share with other sections of the design that may They require the activity through at the cost of retention, element level incremental power consumption, area overhead. Such a system behavior can be realized using a retention strategy representing an SR element of type single control balance latch, both illustrated by the UPF specification in Code 1. Note that while set retention specifies the system level SR strategies at current scope, so the defined retention cell specifies the underlying gate level abstraction of the individual SR element, not detailed herein. Figure 2 is typical power-aware verification setup. And then, legendary like this. And figure 4 is signal level behavior for an LP system. Code 1 is a UPF 3.1 code specifying a single control balloon latch type SR element. So, conventional SR techniques mostly involve the straightforward, simpler implementation of the underlying SR element, such as SR registers or flip-flops and system-level SR strategies that are effective in conventional design paradigms, but are increasingly getting suboptimal for evolving technologies and applications. An example of a signal-level behavior of such a conventional SR technique is illustrated in Figure 4. Involving strategy as shown in Code 4, Code 2, using underlying retention element having the clock signal CLK gated internally with the retention. Control signal RET align the click tree activities when RET remains asserted without causing any malfunction, including loss of retained state. Such an implementation does pose any constraint on the system-level clock tree, allowing each driver to be powered off to the reduced power consumption, though at once the cost of the retention element levels incremental power consumption and area overhead. However, shown in Figure 4, it requires the clock to be frozen at logic 0 level at the save as restore control event for the having the restore functions to operate successfully. The condition for the same is specified using save condition and restore condition options to set retention as shown in Code 2. As the semiconductor process nodes shrink and the device architecture becomes more complex, conventional SR techniques struggle to meet the new demand for a high performance, high power, and higher power efficiency and faster recovery times in the low power area overhead. In this figure, the state of the SR register is maintained during power down, but the recovery time is relatively slow, and the power consumption remains constant due to the static nature of the control signals and activation clocking paths. Additionally, conventional techniques may not fully account for the intricate power domain crossings, reading the potential data integrity issues during power mode transitions. This is a Figure 4 conventional SR behavior, and this is Code 2 UPF 3.1 code specifying a conventional SR behavior in Figure 4. Many of the evolving advanced SR strategies aim to address these shortcomings by incorporating more sophisticated and area and power efficiency SR element with low power, that is device level optimization utilized in building in such element. This optimization includes the use of the low power leakage transducers to improve the retention mechanisms and a more dynamic control of the retention element based on real-time power and performance needs. However, these improvements often may impose additional functional and electrical boundary conditions, such as stricter time requirement for signal transition, more complex interaction between the power domain and the need for a tighter control over clock and sense signals during state mode transitions. An example of the signal level behavioral samples of such advanced SR techniques are illustrated in Figure 5, which, for example, provide a more fine-grained micro architectural level trade-off. Such advanced SR strategies can significantly reduce power consumption while maintaining the fast recovery times by dynamically adjusting retention control signals based on the system operational state. In Figure 5, the additional SR techniques leverage a single control balloon latitude retention strategy where both the clock and the reset signals are managed separately to ensure the optimal power saving during the period of inactivity. This approach allows the system to be selectively power down specific regions while retaining critical data in key areas of the design. For example, Figure 5 illustrates a strategy using the underlying retention element exposing the clock signal's clock CLK without any internal gating, thus imposing a constraint on the system level clock tree to maintain a known as a logic level 0 as this is a restoration when the RLT remains asserted to avoid loss of retention state. However, such an implementation requires additional system level constraint with the benefit of the low power and the low area retention element. Figure 5 illustrates another advanced strategy using underlying the retention element having no internal gating on the clock circuit path, but with a specific circuit level optimization of a SR element that is resilient to operate with an undriven path with the undriven signal CLK by allowing the clock tree drivers to be powered off during the load power mode. With a more fine-grained power-saving element, saving entitlement, like a conventional method, the advanced strategy adapts to varying power and performance demands, making it more suitable for modern application with diverse control conditions such as mobile and embedded system. This strategy is not only optimizing power consumption during the standard mode, but also enable rapid recovery from power down state, thus in ensuring the system resume the full functionality quickly when needed. A. Clock to stay low power RLT asserted. B. Clock to stay low and RLT in asserted. Clock to stay low and undriven due to the driver whose power is off when shut off is asserted. Figure 5 advanced SR behavior. As these advanced SR techniques evolve, they impose new technology challenges in terms of verification and implementation, and the additional boundary conditions introduced by device-level optimization requires more granular control over SR elements, so leading to increased complexity in specifying and verifying power intent, including fine-grained microarchitectural optimization and trade-off to keep the entire clock tree either powered on or powered off during the power down mode. The upcoming UPF 4.0 aims to address these challenges by introducing new features and commands that allow for a more detailed specification of the retention behaviors, power domains, and interaction between them. These enhancements enable designers to model advanced SR strategies more effectively either in the design cycle, ensuring all that functional and electrical constraints are met, even as power management techniques continue to evolve. Chapter 3 Limitations of existing power intent standards. Comprehensive handling of the boundaries conditions imposed by the evolving advanced SR strategies discussed in the earlier section is not supported in the current version of the PI standards. For example, strategy shown in the figure 4 and figure 5.8i and figure 5bi require reset CRRG to make effective if asserted power level event and save the retained state information to be lost. Additionally, there are more nuanced conditions for successful save and store and retention operation as illustrated. In Figure 5, requires the CLK remains low through the entire period between the save and restore event. In Figure 5, requiring the clock to remain powered through the periodic domain between the save event and power down event, between power event and restore event, and the clock to either remain low and driven by low powered off driver during the period between the power down and power up event. Thus, most of the electrical behavior constraint is the reset, clear G, and set reset preset, clock set or preset, and the clock circuit signals of such SR elements of this related to the SR strategy across the different states of the related power domains. Both primary and backup power domains and the state of the retention controller signal are unspecified in the current PI specification standard UPF 3.1 and earlier. This allowed for checks only at save content, save event, and restore the event at a period between the power down and power up event. This state-of-the-art causes either late finding of the basic architecture in infrastructure specification violations and is inappropriate, both inaccurate and incorrect. The implementation details now evolve until very late in the design cycle, as they cannot be comprehended in RTL stage due to the PI limitation with the specification, significant specification and verification gap. Existing synthesis and implementation tools cannot comprehend and hence handle such a requirement and comprehensively due to the aforementioned PI limitations. Typically, such functional behaviors can be comprehended at a mature design stage in PA gate level abstraction, mostly with PA simulations, and some electrical behaviors require event transistor level simulation like analog and mixed signal AMS and code simulation, which can be prohibitively closely and even impractical to be performed due to the complexity and computational cost involved in performing such as simulation, especially starting at a pretty late stage of the design, potentially resulting in escaped design issues and silicon bugs. 4. Advanced retention handling. In proposed UPF 4.0 and the upcoming version of UPM 4.0, we propose to the additional syntactical features supporting the scalable semantics of involving advanced SR requirements and techniques for more complete power intention specification, consistent and coherent interpretation with the seamless handling across the EDA tools and flows. These features include semantic and syntactic extension to existing retention-related command viz, define retention cell and map retention cell, and cell retention supported by the introducing the predefined command options. For example, newly predefined condition to identify the system state viz, save event condition, restore event condition, restore periodic condition, and power down periodic condition. The options save condition, restore condition, and retention conditions are made legacy and cannot be specified consistently and coherently with the newer options. A new option, async cell reset effect, is introduced to specify how the reset and cell signals affect the output and retained value during the restore period, while having no effect on in normal operation. Note that the currently all these enhanced and new options are only for the purposes of verification and have no explicit or uniquely effect on the synthesis and implementation flows. The correctness of implementation depends on the right map retention cell and cell retention cell specified for SR strategies as always. Basic retention register operation and modeling that are useful in describing the simulation semantics for cell retention command is shown below. UPF version 4.0. And the save event condition gate, the save event defining the save behavior of the register. The register content is just saved when the save event occurs in the save event condition is true. The retained value shall be the register value at the time of the save event at the save event condition evaluated true. For edge-sensitive save, the save event is rising or falling edge of the save signal at the specified edge. For level-sensitive save, and the save event is trailing edge of the save signals. The restore event condition gets the store an event from the triggering the restore operation of the register. The register is stored, and the store event occurs as the store event condition is true, and the retained value is transferred to the register, and the stored event and the event store event restore event condition values to be true. The restore event is the rising of the or falling edge of the edge. Trigger the restore signals of the leading the trail and the trailing edge of the level sensitive restore signal. In addition, in the case of the level sensitive restore, the restore operation is continuous throughout the store period and taking value and asynchronous set effect in option into account. The restore period condition also gets a restore operation. The restore operation occurs continuously during the entire restore period. The restore period condition shall be true through the entire restoring period, and otherwise the restoring operation will fail and the retention element will be corrupt. If the restore period condition is not met, is not specified, the restore operation is not gated. So the power down period condition defines the condition under which the retained value is maintained when the power domain is power off, and the power down period condition is specified. It shall evaluate the true the entire time the domain's primary power is off for the value of the stated element to be retained. If the power down period condition evaluated to false and the primary supply is non-normal, the retained value of the state element is corrupted, and the remaining value is affected by the option. The driver supply of any pin listed in the power down period condition shall be at least one the retention supply of the retention strategy. And the save event condition and restore event condition, and restore period condition, and power down period condition shall only reference the predefined name UPF generic clock, UPF generic async set reset, or the logic net output rooted in the current scope. For edge triggered flip-flops, UPF generic clock represents a signal whose rising edge triggers the register to load. For level-sensitive latches, this is a signal whose high value enables the latch. UPF generic and async set reset is expression delivered derived from the set or end reset input of the flip-flops as the following. Set signal normalize the active high, and reset signals normalize the active high. This expression is true when either the set or reset signal is active. For improving the ease of the strategy definition, a new option applies introduced to edge filter to restrict the strategy to apply only a statement element of a given type is floor, latch, any. So 5. Case studies and discussions. This case study demonstrates some practical application of SR strategy in LP design that highlight the design trade-off that enables optimization techniques to minimize area and power overhead while maintaining the rapid recovery of a system state. The clock and reset and set behavior dependencies on the retention functionality of a single control and dual control SR elements are discussed. A single control retention. A single control SR element has just one control signal to indicate whether the register is operating in normal mode or in linear mode. In addition to the standard RTL-defined clock and data and output and set and reset ports, single control SR registers have an additional retention control port that is specified in the set retention command. In this study RTN defined an edge active loop retention control port. A typical retention sequence is as follows. Optionally stop the clock at the specified state clock and assert the retention clock signal RTN. Save the value in the flip-flop and power down, power up, restore the saved value. They assert the retention control signals. In addition, it is recommended to have the clock retain its inactive state and the circuit isolate the output of the domain before the powering down, and prevent unknown values from the propagating from the powered down domain in the input powered up domains. So, a level-sensitive controller signal should be used to specify the restoring of the Q at power up, while an edge trigger's control signal is specified if the Q value required to restore at the end of the retention cycle. Some retention cells require the clock or the reset to be held at a certain value during the specified intervals of retention period, so their requirement can be specified using various condition options in the set retention command. If any of these commands are false at any time during the entire interval, level sensitive or the edge sensitive, the save and restore operation will fail, and the retained value will be set to X. Figure 6 illustrated the behavior of the retention flip-flops under various save and restore conditions, in which UPF generic clock is presented to allow the user to model the retention behavior with respect to the state of the clock. So UPF specification for each of these variants are listed below. In the figure 6, single control retention clock behavior. The A clock signal during the RET inactive, no save event condition, restore event condition, and restore period condition present in the command. B clock must be low at the save and restore event, save event condition, and then C clock must be low at the event at the save event and restore event, and during the restore period. The sharp, the restore period condition applied to both restore event and period, like this. The clock must be during the save and restore event and during the restore power down period. Save event driven UPF generated clock as the restore period condition, UPF generated clock as power down period condition, not UPF generated clock. And the clock must not be high during save and restore event and during the restore and power down period. Clock must be low and save and restore event during the restore period and not high during power down period. Figure 7 shows the retention behavior for various values of async set reset effect. In this figure, the reset is active during the restore period after power up. The figure shows the value of the Q during the restore period, which changes depending on the values of async set reset effect. The UPF specification for each of the variants are listed below. Figure 7 is single control retention, reset behavior. And reset is ignored during the restore period. Async reset is ignored. B reset effect retain the value and therefore the output of the during the period restore period. And async reset effect retain the value. C reset affected the output value during the restore period. Async reset effect output values. B. Dual control retention. A dual control SR element has one signal to indicate the save and a different signal for the restore. When another control signal is active when the register acts normally. In addition to the standard RTL defined clock CLK data D, output Q, and set reset port, dual control SR registers have additional retention control ports with save and restore are specified in the set retention command. A typical retention sequence is as follows. Optionally start the clock at a specified state CLK, save the state by the asserting save signals and the assert save signals, power down, power up, restore saved value by asserting the restore signal, deassert the restore signals. Figure 8 illustrates the behavior of the retention flip-flop under registers save and restore condition and which UPF generic clock is present in those signals. The UPF specified for each of these variants are listed below. And figure 8, dual control retention, clock behavior, and clock ignored. No save event condition, restore event condition, or restore period condition present in the command. Clock must be low at the save and restore event. Clock must be low at the save and restore event and during the restore period. And clock must be low at the save and restore event and during the restore period and during the power down period. Clock must not be high at the save and event during the restore and power down period. F. Clock must be low at the event and during the restore period, but not high during the power down period. Figure 9 shows behavior when the cell is active and both power up before a restore is active and after the power up during the restore signal is active. For case A, when the restore is inactive, the reset signal is always obeyed since the flip-flop is normal mode. However, the restore is active, reset is ignored since asynchronous reset effect is set to ignore, and the second and the third case, B and C, when the flip-flop is in storage mode, the sync set reset effect option takes effect. The signal Q already in the figure below to represent the actual saved values in the circuit. For performance regions, simulators may choose to save the value of the Q at the save event edge sensitive, or use the trailing edge of the save signal level sensitive. Figure 9, dual control, retention, reset behavior. So, chapter 6 is the conclusion. This paper represents a proposed synthetic and semantic enhancement to existing UPF command to support evolving the advanced SR strategies. It throws light on some insight how SR register SR strategies can be effectively implemented to balance energy efficiency, system performance, and data integrity, making it an essential component of modern LP design flows. It presents recommendations on best practices for designing and verifying SR strategies in the current continuously evolving the future energy-aware electrical system. Acknowledge the author thanks to their colleagues of the IEEE 1801 working group for their creativity in devising many of these design examples of this paper. Okay, today I read this paper, The Future Proofing Power Intent Specification through UPF 4.0 for Evolving Advanced State Retention Strategies. Thank you for your time. See you next time.